1 watt of heat changes hands 5 times before it leaves the building. Follow that single watt from a hot chip to the open sky and one box does the trick, the CDU. Here's the problem. A modern AI chip can dump 700 to 1000 watts into a package the size of a postage stamp. A single rack now hits 50 to 130 kilowatts. Move that heat too slowly and the silicon throttles or dies in seconds. So we're going to chase 1 watt across all 5 handoffs. Handoff 1. The chip hands its heat to metal. Heat conducts up through the chip's lid and a thin paste into a metal block pressed right on top. A cold plate. Why liquid and not a fans? Water carries about 3,500 times more heat per gallon than air. That's the whole reason chips this hot went wet. Inside the cold plate are hair-thin channels, microchannels, and cool liquid races through them, brushing right up against the hot metal. Coolant enters at roughly 30 to 40 degrees Celsius, warmer than a swimming pool and leaves hotter. Notice something. The liquid never touches the chip. It only touches the plate. The watt has crossed from silicon into metal. Now it's sitting in a puddle of warm liquid with nowhere to go. So where does that liquid take it next? Handoff 2. The cold plate hands off to a loop of its own. That warmed liquid flows out of the plate into pipes running along the rack and heads downstream toward the CDU. This is a private loop, sealed, clean, and often a treated mix of water and glycol. Here's why it stays private. The building's plumbing is full of minerals and grit that would clog those hair-thin channels in weeks. So this loop is kept walled off from the facility's messy water, its own clean bloodstream just for the chips. And now the watt is riding in moving liquid, not sitting in metal. That changes the rules. To keep the temperature rise small, you push more liquid faster. Flow rate measured in gallons per minute does the heavy lifting. Slow the pump and the same watt makes the liquid hotter. Speed it up and the heat spreads thin. But this clean loop can't dump its heat outside on its own. It has to hand off again to the CDU. Handoff 3 happens inside the box the whole video is named for. This is the CDU's core job. Picture 2 separate loops that never touch, pressed against opposite sides of the same thin metal plates. A plate heat exchanger. The clean chip loop flows down one side. The building's water flows up the other. Heat crosses the metal from hot to cold, but not a single drop mixes. That's the trick. The chip's private loop stays clean forever, while still dumping its heat into the building's supply. The CDU does more than trade heat though. It pumps the clean loop, filters out any stray particles, and constantly watches flow, temperature, and pressure, dialing the pumps up or down to hold everything steady. It also keeps the 2 loops at different pressures, so a leak can't cross over. One quick note. Some smaller CDUs skip the second water loop entirely and blow the heat straight into the room's air with a big radiator. Those are liquid-to-air CDUs. But in a serious AI hall, the CDU hands the watt to water. So where does the building's water carry it? Handoff 4. Now the building's own water carries the watt on a long walk. This is the facility loop, the pipes that run out of the CDU across the building toward the machines that throw heat away. Here's the choice that decides the power bill. That facility water can take a detour through a chiller, basically a giant air conditioner that uses a power-hungry compressor to force the water cold. Or when the weather outside is cool enough, it can skip the compressor entirely and dump its heat straight to the outdoors. That shortcut is called economization. And this is why running the chips warm is a gift. If your loop is happy at 40 degrees Celsius instead of ice cold, the outside air is almost always colder than that. So most of the year you never switch the compressor on at all. The watt gets a nearly free ride to the edge of the building. But it still hasn't actually left. How does a watt escape into open air? Handoff 5. The watt finally leaves the building. The facility water arrives at the roof, at a cooling tower. Watch what happens here, it's clever. The warm water trickles down over slats while a fan pulls air through it, and a little of that water evaporates. Turning water into vapor soaks up a huge amount of heat, the same reason sweat cools your skin. That escaping vapor carries the watt up into the sky. The water that's left behind is now cooler. If a site can't spare the water, it uses a dry cooler instead. Just a giant radiator with fans handing heat to the air with no evaporation and no water lost, though it doesn't cool as deeply. Either way, the watt is now outside, mixed into the atmosphere, gone. And here's the beautiful part. The cooled facility water doesn't stop. It loops right back to the CDU to pick up the next watt. Then the next. This relay never stops running, second after second, for every chip in the hall. So there's the whole relay in one breath. The die hands its heat to the cold plate. The cold plate hands it to the clean chip loop. The clean loop hands it across the CDU's plates to the facility water. The facility water carries it to the cooling tower. And the tower hands it to the open air. 5 handoffs, and the CDU is the exchange point in the middle. The one box that lets a spotless chip loop and the building's messy water trade heat without ever touching. That separation is the quiet genius. It's what lets us pack 1,000 watts onto a stamp-sized chip and still keep it alive. That is how 1 watt leaves the building in 5 handoffs, and why liquid cooling is the thing making today's dense AI compute even possible. Here's the one idea to keep. Cooling isn't a single machine. It's a relay, and heat only ever moves by handing off from one carrier to a cooler one. Metal to liquids, liquid to liquids, liquid to air. The next time you read that a data center runs warm, you'll know that's not sloppiness. It's the whole strategy. A warmer loop means the outside air can do the work for free, and the compressor stays off. Run hot on purpose and the sky does your cooling. So cooling is a relay of handoffs, and the CDU is the exchange window in the middle. But every handoff costs energy, the pumps, the fans, the compressor when it does kick on. Next, we'll count that cost. The power a data center burns just to stay cool, the water it drinks, and how the industry scores both. That's PUE and WUE, and the numbers surprise people.